What I have here is a very simple gravity simulator. It allows me to create a cloud of particles with different initial conditions and then observe how the system evolves as gravity does its job. We usually think computers are really good at simulating things, but the truth is that their performance depends heavily on the algorithms we use. Here, for example, as I increase the initial number of particles, the program stops rendering smoothly. This happens because my algorithm calculates how every particle is influenced by every other particle in the system, meaning its time complexity is O(n) squared. Now, there are dozens of different ways to speed this up, but in this video, I'm going to talk about a hardware feature called SIMD, which allows us to perform certain tasks in parallel without needing additional threads or processor cores. Hi friends, my name is George, and this is CodeCrafters. This video was sponsored by Let's Get Rusty. More about them later in the video. When we want a computer to perform a mathematical operation, such as addition, we write it as a single line of code. But as I've said countless times before, the processor may need to execute several instructions to make that operation happen. Normally, when computers perform arithmetic, they rely on a group of general-purpose registers whose size is usually related to the architecture. A 16-bit processor typically has 16-bit general-purpose registers. A 32-bit processor has 32-bit general-purpose registers, and so on. The size of these registers determines how many bits the processor can conveniently operate on at once. A 32-bit system, for instance, cannot normally add two 64-bit numbers in a single basic operation. Instead, it has to process them in smaller pieces, usually 32 bits at a time, requiring multiple steps. What we are going to explore today is kind of the opposite idea. Modern processors have another kind of register known as a vector register. These registers are much wider than general-purpose registers, and instead of using all those bits to represent one enormous number, they can be used to hold and operate on multiple smaller numbers at once. That is essentially the idea behind SIMD. SIMD stands for Single Instruction Multiple Data. It relies on wide vector registers whose contents can be interpreted as multiple smaller independent elements, usually called lanes. So we are free to decide how the information in such huge registers should be interpreted. A single instruction can then perform the same operation on all those lanes at the same time. A 128-bit vector register, for instance, can hold 4 32-bit values, 8 16-bit values, or 16 8-bit values. If you think about it, this is very useful because it is essentially a form of parallelism that does not require us to create additional threads or rely on additional processing cores. Operations like this, where multiple values are packed into a vector register and the same operation is performed on all of them, are commonly called packed operations. However, SIMD has one major limitation. We can divide the data into multiple lanes, but the operation performed by a SIMD instruction is generally the same for every lane, hence the name Single Instruction Multiple Data. Notice that I'm not saying SIMD is limited to a single type of operation. Different operations can be performed one after another. The limitation is that each individual instruction performs the same operation across all lanes at once. You see, at this level of abstraction, CPU instructions are supposed to describe relatively simple operations. In the same way that it is simple to tell the CPU, add these two numbers, it is also relatively simple to tell it, add all these pairs of numbers. But telling it to add the values in one lane, multiply the values in another, divide the next ones, and subtract the next ones is a very different problem. With only 4 possible operations and 4 lanes, there would already be 4 to the power of 4, or 256 different combinations of operations. With 32 lanes, there would be 4 to the power of 32 possible combinations, and that is considering only addition, subtraction, multiplication, and division. Real processors support many more operations. Now, this does not mean it is physically impossible to build hardware where different lanes perform different operations. The problem is that doing so would require much more complicated instruction encoding and control hardware, while defeating much of the simplicity that makes SIMD efficient in the first place. So SIMD hardware is designed around the idea that we have lots of different data that needs the same operation. Now you might be wondering, how does the CPU know how the vector register should be interpreted? How does it know into how many lanes it should split the vector register? As expected, that information comes from the instruction itself. Encoding formats depends on the architecture, So let's look at how this works with x86-64 SIMD instructions. With the AVX family of instructions, many vector instructions begin with a VP or V, which indicates that we are dealing with a vector-packed operation. The name of the vector register tells us how wide the register is. XMM registers are 128 bits wide, YMM registers are 256 bits wide, and ZMM registers are 512 bits wide. Then the instruction itself tells the processor how the contents of that register should be interpreted. In assembly, the instruction has a suffix. For integer operations, for example, B means byte, or 8-bit integers. W means word, or 16-bit integers. D means double word, or 32-bit integers. And Q means quad word, or 64-bit integers. While PS and PD are used for floating point numbers. So the register tells the CPU how many total bits we are working with, while the instruction tells it how those bits should be interpreted. From those two pieces of information, it gets the number of lanes. There is something important to consider though. Not every operation exists for every data type. For example, x86-64 has packed multiplication instructions for several integer widths, but it does not provide a straightforward packed 8-bit multiplication instruction. This is because multiplication between 8-bit integers is very likely to overflow. When 8-bit values need to be multiplied, they are commonly widened first and then multiplied using wider lanes. With division, the situation is a little different. Integer division is a relatively complicated and slow operation in hardware. Replicating enough integer divider capability to efficiently process many SIMD lanes would consume significant silicon area for an operation that appears much less frequently than addition, subtraction, or multiplication. So packed division is only implemented for floating point numbers. Now, before we get into the simulation example, I need to explain something else. If you follow this channel, I'm pretty sure you love low-level systems, and that's exactly why I'm excited to say that this video is sponsored by Let's Get Rusty. Big companies are betting big on Rust for building critical systems. Google, Microsoft, even the Linux kernel itself are now integrating Rust into their core systems. That's not hype, that's happening. And if you're thinking about leveling up your Rust skills, whether for personal growth or to land a job working on real systems, Let's Get Rusty is the go-to place for Rust training. Created by a fellow YouTuber and one of the most beloved names in the Rust online community, Let's Get Rusty has helped thousands of developers, myself included by the way, master the language and break into systems programming. They're running a new cohort very soon, and since spots are limited, now's a great time to check it out. Visit letsgetrusty.com/startwithgeorge, or just click the link in the pinned comment below. And now, back to the video. As I was saying, there's one thing we should talk about before showing the simulation example. Whenever we operate on data inside registers, that data usually has to be loaded from memory first. And of course, vector registers also have instructions for loading large blocks of data from memory. A 256-bit load, for example, can fetch 256 contiguous bits from memory into a YMM register. This works extremely well if all the values we want are sitting next to each other in memory. But that introduces an important caveat. What if they aren't? If the values we want are scattered throughout memory, a simple contiguous vector load cannot fetch all of them at once. There are ways around this. We could perform multiple loads and rearrange the data with shuffle instructions, or on supported instruction sets we could use something known as a gather instruction, which can collect values from multiple memory locations into a vector register. But these approaches require additional work and can reduce some of the performance we are trying to gain from doing the arithmetic in parallel. So when working with SIMD for performance, the way our data is organized in memory matters a lot. And that brings us back to the gravity simulation. For educational purposes, I've chosen the simplest, but also one of the most inefficient approaches, calculating how every particle interacts with every other particle in the system. As you might have heard, gravity is produced by mass. Let's consider two particles. We'll call them I and J. Their masses produce a gravitational attraction between them. And according to Newton's law of universal gravitation, the magnitude of that force is proportional to the product of their masses and inversely proportional to the square of the distance between them, multiplied by the gravitational constant g. Now, since our goal is to determine the position of each particle as time passes, What we are really interested in is how this gravitational force makes each particle accelerate. From Newton's second law, we know that force equals mass times acceleration. If we combine that with the gravitational equation, we find that the acceleration produced on particle I by particle j is proportional to the mass of j, and inversely proportional to the square of the distance between them. In other words, the more massive j is, the greater the acceleration it produces on I. But as the distance between them increases, that acceleration rapidly decreases. And because we are working in 2 dimensions, acceleration is not just a number. It is a vector. It has a horizontal component and a vertical component. Once we know that acceleration, we can use it over a small time step to update the particle's velocity and then its position in both axes. And that's how we know where to draw the particle when updating the screen. And of course, we also need to determine how the gravity produced by I influences j. Easy, right? Well, things get more interesting as we increase the number of particles. Particle I is not affected by only one other particle anymore. It is affected by the gravitational influence of every other particle in the system, each one accelerating it with a different magnitude and in a different direction. A particle cannot independently follow all of those accelerations at once. But because acceleration is a vector, we can simply add all those acceleration vectors together to obtain the net acceleration of the particle. If the particle is initially stationary, that acceleration will cause it to start moving towards that direction. If it is already moving, its velocity will change according to that acceleration. So what the simulation does is calculate the net acceleration of every particle produced by all the other particles in the system. Once those accelerations have been calculated, we update the velocity and position of every particle. And as soon as all the particle positions have been updated, the process starts all over again. Because the particles have moved, the distances between them have changed. That means their gravitational interactions have changed, which means the acceleration vectors we calculated before are no longer valid and need to be calculated again. And for us to perceive this as smooth gravitational motion, this entire process needs to happen really fast. Of course, to make things more interesting, the simulation also detects collisions and merges particles together, creating more massive objects that cause smaller ones to start orbiting around them. I won't go into how that part works because it's not the main topic of the video, but I'll leave a link in the description in case you want to play around with the code. The problem, as I mentioned in the intro, is that at some point the particle count becomes so high that my computer can no longer perform all of these calculations fast enough for the simulation to evolve smoothly in real time. So our goal now is to speed it up using SIMD instructions. At any given moment, a particle has a horizontal and vertical position, a horizontal and vertical velocity, and a mass. If we take a closer look at the gravity calculation, before we can even calculate the acceleration produced by another particle, we first need to determine the distance between them. And to calculate that distance, we need their horizontal and vertical separation. Fortunately, calculating these values is a very trivial task. What I want you to notice here is how many arithmetic operations are involved to get these values. First, we need one subtraction to calculate the horizontal difference between the two particles. Then another subtraction to calculate the vertical difference. We need 2 multiplications to square those 2 values. Then an addition to add those squares together. And finally, a square root to obtain the distance. That is already 6 arithmetic operations, just to determine the distance between one pair of particles before we can even start calculating the acceleration. And remember, we have to repeat this and all the following steps for every interaction. If we have n particles, each particle has to consider the other n-1 particles. And this is where SIMD becomes very interesting. I don't want to redesign my simulation, I just want to make it faster. Instead of calculating the horizontal distance between particle I and particle j, one particle at a time, what if we calculate the horizontal distance between I and several other particles simultaneously? If our positions are stored as 32-bit single-precision floating point numbers, a 256-bit vector register can hold 8 positions at once. So we could take the x-coordinate of particle I, place copies of it across all 8 lanes of one vector register, load the x-coordinates of 8 other particles into another register, and subtract them. 1 SIMD subtraction. 8 horizontal distances calculated at once. There is only one problem. Our data might not be organized in memory in a way that makes this easy. If I have a program that simulates particles, the most natural way to represent them might look something like this. A particle is a structure containing an x position, a y position, an x velocity, a y velocity, and a mass. And then the entire system is simply an array of these particle structures. From a programming perspective, it makes perfect sense. Everything belonging to one particle is stored together. The problem is that the values we want to operate on are scattered throughout memory. When I want the x coordinates of 8 different particles, those values are not next to each other in memory. And for SIMD, we often want exactly the opposite, the same property from many particles stored next to each other. So this separation is bad not only for loading data into vector registers, but also for cache efficiency, because modern CPUs usually don't fetch only the exact value we request from memory. Instead, they load an entire nearby region of memory, called a cache line, into the CPU cache. With an array of structures, if we only need the x coordinates, those cache lines also bring in nearby values like the y coordinates, velocities, and masses, so a lot of the data being loaded is not useful for the current operation. And because fewer of the values we actually need fit into each cache line, the CPU may have to fetch new cache lines from memory, more often just to gather those scattered x coordinates. The solution is a little awkward. Instead of using an array of structures, we can use a structure of arrays. Now we have one array containing every x position, another array containing every y position, another containing every x velocity, another for the y velocities, and another for the masses. The properties belonging to one particle are now separated in memory, but the same property from many different particles is stored sequentially. And that is exactly what we want, both for SIMD and for cache efficiency. More of the values we actually need can fit into the same cache line, and because those values are contiguous in memory, they can also be loaded directly into vector registers much more efficiently. Now the processor can load 8 x coordinates with a single contiguous vector load and operate on all of them at once. In this particular example, where I'm considering only 9 particles, particle I interacts with 8 other particles. That happens to fit perfectly inside a 256-bit vector when we are using 32-bit floating point values. So once the values are loaded, all 8 horizontal differences can be calculated with a single vector subtraction. If we increase the system to hundreds or thousands of particles, they will no longer fit inside a single vector register. But that is not a problem. We simply process them in batches. 8 particles, then another 8, then another 8, and so on. It is still much better than processing every interaction individually. In this example, after getting all the horizontal differences, 8 vertical differences can be calculated with another vector subtraction. If computing a value requires more than one arithmetic step, the intermediate results can be stored in arrays in memory, or, when possible, kept directly in vector registers as we continue through the calculation, allowing the following operations to process all 8 interactions in parallel as well. If we use this approach to parallelize the gravity interaction computations as much as possible, all the way up to calculating the updated positions of the particles, we get this. Again, the interactions are still calculated in exactly the same way, and the complexity remains O(n) squared. We're not reducing the amount of work the simulation has to do, we're just making better use of the hardware to perform that work faster. If we increase the number of particles even further, even the SIMD version starts to struggle. Something I consider strange about SIMD is that the instructions themselves are actually pretty simple and intuitive, as we saw earlier in the video. The difficult part is restructuring the algorithm and its data so those instructions can actually be used efficiently. Sometimes that means changing something as fundamental as how data is laid out in memory. Algorithms that look perfectly natural when written normally may need to be reorganized in slightly awkward ways so that, at runtime, the values we want to process together are also stored together. The good news is that we don't always have to write SIMD-specific code ourselves. Modern compiler optimization techniques are quite good at recognizing common patterns that can be executed with SIMD. This process is called auto-vectorization. Instead of generating scalar instructions that process one value at a time, the compiler can automatically generate vector instructions that process several values at once, assuming, of course, that optimizations are enabled, and the code is structured in a way that makes vectorization possible. There are several common patterns that compilers are particularly good at recognizing and vectorizing. Unfortunately, this video is already getting pretty long, so I'm not going to explain all of them here. But let me know in the comments if you'd like a separate video about how compilers recognize these patterns and turn ordinary code into SIMD instructions. Finally, there's one more thing I want to mention that often gets left out when talking about SIMD instructions. Modern CPUs don't have just one execution core. They have multiple cores capable of running code in parallel, and each core has its own vector execution resources. So SIMD and multi-threading are not competing forms of parallelism. We can actually use both at the same time. Different threads can run on different cores, while each of those cores is simultaneously executing SIMD instructions. This gives us two levels of parallelism: multiple cores executing different work in parallel, and multiple SIMD lanes processing several values at once inside each core. In a very idealized case, you might imagine the available parallelism scaling roughly with the number of cores multiplied by the number of SIMD lanes. But actually achieving anything close to that performance increase is much harder. Once multiple threads are involved, we no longer have to think only about how data is organized in memory. We also have to think about how work is divided between threads. And whenever threads need to coordinate with each other, some of that theoretical parallelism is lost. So while combining multi-threading and SIMD can be extremely powerful, getting the most out of both requires much more careful algorithm design. And that's it for now. If you want to suggest topics for future videos, feel free to leave a comment. Don't forget to check the sponsors in the description below. Or consider subscribing. And if you liked this video or learned something new, please hit the like button. It's free, and that would help me a lot. See you in the next one.